In this lecture, I will discuss electromagnetism. I will talk about the basic properties of magnetic materials, simple magnets, magnetic poles, magnetic field lines, and then I will discuss the interaction between magnetic particles and currents, electric currents. I will also talk about transformers, and I will also talk about charged particles that are moving in magnetic fields. Most of us have played with magnets. Through play, we learn that these little pieces of material attract and repel each other, and that they attract some objects but have no effect on others. For instance, magnets stick to refrigerator doors but not to the walls of a room, to paper clips but not to paper, and so on. Although magnetic properties are interesting, they, like electricity, appear to be rather isolated phenomena. Unlike electricity, however, magnetism does seem more permanent. And although there are similarities between those two phenomena, they seem to be separate properties of matter. A magnet with no net electric charge does not deflect the foils of an electroscope. So magnetism appears to be a different phenomenon from electricity. However, some experimenters in the 17th century were more fascinated by the similarities between magnetism and electricity than their differences, and so they searched for a connection. This connection culminated in the work of Maxwell, who came up with the electromagnetic equations which explain the interaction between the electric and magnetic fields in nature. First, let's start with magnets. Magnetic materials have been known to humankind for centuries. The earliest known magnetic material is magnetite. Magnetite is also known historically as lodestone. This naturally magnetic mineral attracts iron and magnetizes it. The magnetized piece of iron then attracts other pieces of iron or other metals that contain iron. There are several other naturally occurring magnetic materials. Those are cobalt and nickel. A magnet is a piece of magnetic material, typically in the shape of a bar or a horseshoe. A magnet has two distinct magnetic polarities at each end. We have a north pole, which we label with capital N, and we have a south pole, which we label with capital S. By experimenting, people have found that when two magnets are facing each other with opposite poles, like shown here, there is an attractive force that arises between the magnets. However, if we place two magnets with the same poles facing each other, like shown here, then a repulsive force appears between the magnets. And so a general rule can be stated that like poles repel and unlike poles attract. One more time, like poles repel and unlike poles attract. This behavior is very similar to the behavior of electric charges. We know that opposite charges attract and like charges repel. However, the question is there such a thing as a magnetic charge in existence that would explain the behavior of the magnets? Such a magnetic charge would be called magnetic monopole. And a way to determine if such magnetic monopoles exist is to start breaking down a magnet into smaller pieces. The hope here is that breaking magnet into smaller pieces would separate the south from the north pole of a magnet. Suppose we try to separate the poles of a magnet by breaking the magnet in half. What will happen is we'll get two magnets, and each of those two new magnets will have two poles, south and north, and then at the break the other piece will have a south pole and a north pole. So notice how the two poles here are opposite at the point of the break. And so if you were to connect the two pieces back together, those two poles will attract, and of course eventually when the two pieces are together they will also vanish effectively. However, if you break those pieces into smaller pieces, you will end up with 4 magnets, and they will all have a south and a north pole. And so keep on breaking the magnets like that. Results in creating just smaller magnets with south and north poles. It does not seem possible to isolate a single magnetic pole, or in other words, a magnetic monopole. So many extensive experiments have been performed so far in search of such magnetic monopoles, but so far one hasn't been discovered. The existence of magnetic monopoles is not ruled out by now. The theoretical research does not forbid the existence of such monopoles. However, experimentally they haven't been discovered yet. The naming of the ends or poles of the magnets was done based on the observation that a freely swinging magnet aligns itself along the north-south direction of the Earth. The end that points north is called north, and the other is called south. The compasses used for navigation are simply tiny magnets that are free to rotate. And as we already said, a magnet has the two poles, south and north, and so the north pole of the magnet points towards the north pole of Earth, but that's the geographic north pole, and the south pole of the magnet points towards the geographic south. However, from before, we know that when two magnets are meeting each other with opposite poles, they attract. And when two magnets meet each other with the same poles, they repel. So that means that for a compass needle to point in north direction, then the geographic north of the Earth is actually the magnetic south of the Earth. So you can think of the Earth as having a giant magnet inside. Of course, this is just for visualization purposes. And so the south pole of this giant magnet inside is located at the north geographic pole of Earth. And the north pole of the magnet inside the Earth is located at the geographic south of Earth. And so the compass needle will point with its north pole towards the geographic north, which is the magnetic south, and the south pole of the compass needle will point towards the geographic south, which is the magnetic north. So how does the magnetic field of Earth, how is it generated? The theory is that the core of the Earth contains a lot of iron, and the core itself is also in rotation. And so that rotation, that movement of the atoms of the iron causes the generation of electric current, and as we will see soon, electric current generates magnetic field. So the magnetic field of the Earth is generated by the rotation of the Earth's core. The magnetic field of Earth is actually extremely important because it creates a magnetic field shield around the Earth that is very successful in deflecting cosmic radiation, and more specifically, charged particles that are coming from the sun. We know from some experience with magnets that magnets interact from distance. And we also know that the closer you bring two magnets together, the stronger the magnetic force between the two magnets gets, and the further away you bring the magnets, the smaller the magnetic force between the magnets. Now we know from our discussion on electric charges that when the interaction happens from a distance, that involves a certain type of field that surrounds the charges. Well, the same applies for magnets, and so the field that surrounds a magnet is known as magnetic field. The easiest way to visualize a magnetic field is to place a magnet, for example a bar magnet, on a flat surface on which there are iron shavings. And so the iron shavings, which essentially are tiny magnets, will orient themselves along the magnetic field lines created by the bar magnet. And so this looks like so. This is the bar magnet. And you can see how the iron shavings are arranged along this pattern around the bar magnet. So then, schematically, this can be represented with giving direction to the magnetic field lines along which these shavings are arranged, and also indicating the poles of the magnet. And so this is the schematic representation of the magnet and its magnetic field. So the magnet is oriented with the north pole facing up, the south pole is facing down, and as you can see, the magnetic field lines start from the north pole and curve away until they end at the south pole. So this is an important difference in comparison to electric charges. For electric charges, we know that the electric field either radiates out or towards a charge, depending on whether the charge is positive or negative. But the field lines do not start and end at the same charge. Now for magnets, the magnetic field lines radiate away from the North Pole, but curve around and end at the South Pole of the magnet. So the magnetic field lines are not shared between separate magnets. The magnetic field lines are or belong to the same magnet. Another way to map the magnetic field lines would be to use a simple compass. If I place my compass somewhere here, for example, the south pole of the compass will point towards the north pole of the magnet, and the north pole of the compass will point, of course, away from the magnet. And so we know that the magnetic field lines, by convention, that's what we select, have direction away from the North Pole. So then the direction in which the compass points as we move it around will help us map the magnetic field lines. And so if I can use a compass to map all the field lines that this magnet produces. Even though I said that, unlike with electricity where we have two distinct electric charges, positive and negative charges, for magnets we do not have magnetic monopoles, there is a relationship between electricity and magnetism. And this relationship comes from the electric current. Although electricity and magnetism were well known for centuries, any connection between the two phenomena eluded experimenters until the 19th century. In 1820, Hans Christian Ørsted, a Danish physicist, discovered a connection while performing a lecture demonstration. A compass needle experiences a force when it is brought near a current-carrying wire. This means that the current-carrying wire produces a magnetic field in the surrounding space. And so when you bring the compass close to the current-carrying wire, the magnetic field of the wire and the magnetic field of the compass will interact with each other. As a result, the compass needle moves. This discovery was very fascinating, and at the same time it was confusing because it was well known that stationary charges did not produce magnetic fields. So that means that the motion of the charges must have produced the field that Ørsted experienced by bringing the compass needle close to the current-carrying wire. And indeed, a current-carrying wire, shown right here, is placed so that, or positioned so that it passes through a horizontal plate on which we have iron shavings. And so when the current in the wire is turned on, the shavings arrange along those concentric circular lines like so. And it turns out that these concentric lines are the magnetic field lines of the current in the wire. Okay, but we know that the magnetic field lines have direction. In the case of a bar magnet, the magnetic field lines start from the North Pole and then curve around to end at the South Pole. But a current-carrying wire is not a magnet in the sense that we understand magnets. So then, how do we determine the direction in which the magnetic field lines, due to that current, are oriented? Well, for a current-carrying wire, where the current is going towards the hole in the plate, so if that's top view, the current is going down, the orientation of the magnetic field lines is counterclockwise. Clockwise. Okay, but how do we determine that direction? And also, what will happen if the current is flowing in the other direction, from the opening in the plate up on the wire? Well, the rule that I'm going to use to determine the direction of the magnetic field lines for a wire carrying current is, again, the right-hand rule. The direction of the magnetic field is given by the right-hand rule, as I said on the previous slide. So if your thumb points in the direction of the current in the wire, your fingers will encircle the wire in the direction of the field. So in this example, the thumb points up in the direction of the current, the fingers curl around the wire, so the magnetic field direction is counterclockwise. So here is my wire, the current is flowing up. Using the right-hand rule explained here, the magnetic field lines are these concentric circles that have orientation counterclockwise, and this is given by the arrows that I have here. Now, it's important to understand that for a wire that carries current, there are many magnetic field lines, and it's not only those in that plane, so there are many above and below, so they essentially form like a cylindrical shell, if you will, around the wire. And the shell starts from the surface of the wire and goes all the way to infinity, technically. And the further away we get from the wire, the weaker the magnetic field of that current. So, magnetic field is a vector quantity, and the vector that represents the magnetic field is a tangent to these magnetic field lines. And we labeled the magnetic field vector with B. So at any point of the field lines, the magnetic field vector is tangent to the field lines. Now let's also show the example when the current is flowing in the opposite direction in the wire. When the current flows down the wire like so, if you wrap your hand around the wire so that your thumb points in the direction of the current, then your fingers will circle in clockwise direction, and that indicates the direction of the magnetic field of this current. And here on the drawing, of course, I'm using arrows to indicate the direction. The magnetic field vector is tangent to the field lines, and of course now the direction is essentially reversed compared to the above drawing, because the magnetic field lines rotate in opposite direction. So now that we know that a magnet produces magnetic field and we can map that magnetic field, we can go back and explain why the magnetic field of Earth is so important. As I said already, it protects the Earth from the harmful effect of charged particles from cosmic radiation, and mainly from the solar wind. This is an image simulation produced by the European Space Agency that maps the magnetic field of Earth. As you can see, the magnetic field is generated from the core. As I said, you can think of inside the Earth we have a magnet, a bar magnet, and so the magnetic field lines start from the North Pole, which is right here, and curve around until they land on the South Pole. So then the magnetic field will meet the charged particles that are coming from the sun and in general from space. And as we will find out soon, charged particles interact with magnetic fields. They start to move in a particular way. And so what happens here is the particles will hit the magnetic field, and they are going to get deflected, and they are going to flow, depending on what charge they have, either towards the north geographic pole or the south geographic pole. And then as a result, we observe the northern lights or the southern lights. This is an image of the northern lights from the Earth's surface, and this is an image above the atmosphere from the International Space Station. So why do we get these, nice, beautiful colors here? These colors appear from the interaction of these charged particles that end at the two poles with the Earth's atmosphere. So when the charged particles interact with the molecules of the air, lots of energy is generated, and depending on the amount of energy that's generated, and also the angle with which these lights are viewed, we get different colors to appear. What would happen if there were no magnetic field of Earth? Well, the solar wind, which even though it might seem like nothing, and especially since the magnetic field protects Earth from it, will actually blow away the atmosphere of Earth. Imagine a constant bombardment with charged particles of the molecules of the air or the atmosphere. And over the billions of years of evolution of Earth, that solar wind would win, and so there will be no atmosphere on Earth, and therefore life would be impossible. So the magnetic field is very important. And without it, there will be no life on Earth. Another interesting fact to talk about is that the magnetic field polarity of Earth switches periodically. What does that mean? It means that over a certain amount of time, the north and south magnetic poles switch position. So currently the south magnetic pole is at the north geographic pole. Actually, it's a little bit shifted. And the north magnetic pole is close to the south geographic pole. But over the millennia, millions of years actually, the two poles would switch position. And the rough estimation is that this change in position happens roughly 150,000 years. So every 150,000 years or so, the poles switch position. And so the question here becomes, how does that happen? Meaning, is it a quick change or does it take some time? And then what happens to the magnetic field of Earth in between or during the change? And of course, we cannot answer these questions because there's no way to know. What we know is that the last change in the polarity of the magnetic field of Earth happened about 150 or so thousand years ago. So technically, the change can happen at any moment, or it can happen after another 100,000 years. Nobody can say.